Welcome to lecture 4. This time we'll try something different. There will be more theoretical material and less programming. For this lecture, you will need to understand the binary representation of numbers. Let's begin with an example. If, let's say, we have number 5, and we only have 2 digits to use, which is zeros and ones, we can still write down number 5 as 101. This gives us 5. Think of it is like this. The number is a mathematical entity on its own. Like we can select 5 objects. The way that we write this number historically originated that we have 10 fingers. So we use 10 digits to represent each digits in a placeholder. In computers, they use binary system. So just zeros and ones. We have to be able to convert one system to the other. Note how the number itself does not change. It's just a visual representation that changes. If you feel like you're not confident with different representations of different bases for numbering system, please read about it. We will start with a short example. It's going to be a FORTRAN code that will count from 0 and forward. Why cannot this go on forever? Computers are limited in their size. So they're limited by many factors. One is how many sort of like gigabytes of memory you have, or how many gigabytes of hard drive you have. So obviously there's a certain limit on how much you can put in the computer. There's no way it will go on forever, because if we take it to like the very extremes, when we start adding the numbers one by one by one by one, at some point we will reach a number big enough to exceed like the number of particles in the universe, and so on and so on. Now obviously there's certain smaller limits in the computers. You probably heard about 16-bit, 32-bit, and we will start with integers. Again, here's this simple example. It starts with 0. I have the integer value k declared, and there's also k old. First k old is assigned to the k, then the k is incremented, and then we test what happened. Did the k become bigger than k old? If it did not, if it remained the same or it became smaller for some reason, then we stop and we print out k, we print out old k, and we also use this write statement to print out the binary representation of k. The exit command, it terminates the loop. Let's run it. T1 takes some time, computes, it's thinking. It's thinking. Okay, the old value, the maximum value that we achieved here is this. It's 2 billion something. This is the number. Let's take 2 to the power of 31 and subtract 1. This is the number. How do we get it? The variable in the system is represented with bytes and bits. Now each byte has 8 bits. We have 4 bytes for the variable, which makes it 32 bits. In the binary, this is the largest value that it gets. So all ones except for the 0 on the left. By the way, we need some agreement here, which bits we will call the first ones and which will be subsequent ones. So let's do this. We'll start to count them from right to left, and we'll be counting them from 0. So we'll be like 0, 1, 2, 3, all the way to 31. The ones on the right we will also call the least significant ones, and the one on the left, the most significant. Let's look at the number k. It is a negative number. The number itself is different. You see there's 8 in the end, while the other one was 7. So something is going on here as well. Obviously, it's a representation of the negative number. The question is why it is like this. And how does this happen? So there's a more general question that we need to ask ourselves. This feature or this problem with the numbers, is this a feature of the programming language or the operating system, or maybe even something more fundamental? It's like the way that the processor, the CPU, works. And this isn't very obvious, because if I choose some different software, I can clearly work with much bigger numbers. Let's take Mathematica, and I will assign to k something like 10 to the power of 100. And there's absolutely no problem with this. I can even increment k. Let's say k plus 1. And there it is. So interestingly, in Mathematica, there's no problem like that. Now I'm going to show one more example. I have this LibreOffice Calc software. And we'll do something like this. I will put 1 in one cell. In the other cell, I will put 1 to the power of minus 1 times 10 to the power of minus 14. I will add them. Now I'm going to extend this. This one is still there. I'm going to format the cell differently. I'm going to make it so that it shows me 17 decimal places. And clearly the cells add, but by the time I put one more 0 in there, so 1 plus 10 to the minus 15th, it does not add. So it's another strange feature. Something strange is going on there, obviously, and we need to talk about it and discuss it, because when you compute something, you should be aware of what's going on. You should know the limits that you're trying to push. And if you expect, one thing from this algebraic operation, but you don't get really, the computer gives you something different, then it's an error that it's very hard to catch, because you're thinking the computer is doing something, but in reality, your numbers are all just messed up because it's the way your software or your hardware works. Let's talk about the representation of the negative numbers, because with the positive, we are more or less clear. So we have this binary system, and up until 2 to the power 31, so until the 31 bits are filled, we're pretty much good. As soon as we add one more digit to the maximal value, it kind of flips over all the way to the smallest possible value. So this representation, with the leftmost bit being 1, gives us the smallest possible number. Now it's easy kind of like to think that maybe that very last bit, maybe it's a sign bit, that it somehow creates the negative value. But if this were the case, this would be minus 0, which is not. This number is this. Now, what will happen if we add 1 to it? Let's try to do this in the code. I will comment out this whole loop, and I'll just assign k to that value that we got, and I will increment it. And similarly, we will now just print it out in two forms. So we'll print it out in the binary form, and we'll print it out in the decimal form. This is now something very interesting, which I did not expect myself. If I try to assign that particular value to k, the compiler throws an error. It tells the integer is too big for its kind. In fact, that integer is very small though, because it's negative. Let's experiment a little bit, and let's make it 47 in the end. Also, let's print it out before it's incremented. This works as expected. This is the value that we assigned, and the moment we increment it, it goes up by 1, and the binary form is also expected. Pause the video right here and think about the following. What is going to be the binary representation of -1? We'll have the answer in a moment. But before we get to that, I want to try another thing. So we have this k, which compiler accepts. Let's subtract 1. And yeah, we'll see if we can get our value back. And yes, strangely, that works completely fine. So we have a very interesting compiler error that says integer is too big for its kind, only when it's the lowest possible integer. There is definitely a glitch of some sort. Now let's get back to the question, what's going to happen if there will be -1? So we'll just assign k to be -1, and we'll print it in two ways. Again, the decimal and the binary form. Compile, print out, and obviously enough, not surprisingly, all 32 bits are set to 1s. Now, what do you think will happen if I add 1 to this number? Now the addition rule works the same as for the decimal system. So let's say there is some sort of number that I already have, 101, and I want to add 1 to that. What's going to happen? I start from the right, and I get 1 plus 1, which becomes 0, and additional 1 moves to the next digit, so that makes it 10, and I continue adding. The next digit here is 0, which does not change anything, and the next digit is 1. Now, if you apply this addition rule to this number where everything is 1s, and remember, the very last one we cannot carry on because we only have 32 bits. The moment you're trying to carry on to the 33rd bit, it just doesn't exist, and this whole number flips over. Same as the odometer in old cars that would flip over once you reach 100,000 kilometers. The mystery is solved. Now, this is fairly simple with the integers. If you still don't get the idea, read about it. Keep in mind that there may be other representations of the negative values. After all, nobody prohibits you from designing your own processor or your own piece of software that will represent negative numbers in a different way in the binary. Different systems existed in the past, and maybe they even still exist in some systems today. The one that we see here, of course, is the most common. There will be some questions about this on the tests. So this is the topic that you need to know, how the negative integers work in computers. We'll do one more thing. We'll run much older Fortran on a much older machine. So that machine is PDP-11. It's the monster designed in the 70s. I don't have the actual thing, of course, but I have it emulated. Now, this system is not Linux. It's much older than that. So the commands are different, and we are going to list all the files with the 4 extension. Now, this is the way older variety of Fortran, which is called FORTRAN IV, or sometimes it's called FORTRAN 66. It's the one that used punched cards. This is the machine that encodes the punched cards. And if you zoom in on that keyboard, it has some symbols, it has numbers on this right side. So on the right hand side, there's numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's ampersand symbol on P. But this machine did not have lesser or greater symbols at all, and that explains that syntax for the Fortran is dot GE dot for greater, and so on and so on. And then in this code, it actually does use that. So let's look at the code. So I have 2 variables here, I and j. This will be like for my older and newer values. So I start with 0 and I will be incrementing I. And again, this one does not have do loops. Well, it has do loop, but it's not the same. I had to use a go to statement. Now here the point is, there's a label 100. Eventually the loop will come back to this label. We assign the old value to j. We increment I, and then we use this conditional statement if to compare lesser or equal. Basically, it means if I did not increment as we expected, then go out of the loop. Go to the label 200. So jump out. If everything works as expected, if we're incrementing, just keep looping. So go to label 100 and just keep doing this. Now, these days, we don't use go-to statements anymore because this is considered to be a breaking of the structured code. However, go-to statements is how the processor works. So if we have the CPU inside its command system, there is no do loops, but there is a comparison operator and the jump statement. And in the past, programmers, when they designed the programming language like Fortran 4, this is what they saw that it should be. Once our condition is met, once something happens, we print out I, this is the new value, we print out j, it's the one before, and then we have a couple of format statements. These actually do nothing. Format statements by itself, they don't do anything. It's just like an instruction for the type command, how to format things. And so finally, let's run it. And there it is. So not very surprising, but maybe a little bit surprising. So these numbers are smaller, so much smaller. So first look at the maximum that was achieved, 32,767. The one that we had in the 32-bit system is 2 to the power 31. What we have now in the 16-bit system is 2 to the power of 15 minus 1. So that makes it 32,767. There it is. And not surprisingly, so the other one it's 2 to the power 15, exactly. So let's discuss why these numbers are different, why the other one is 68 and the other one is 67. Now, in this 16-bit system, the total number of combinations that 16-bit can give us is 2 to the power of 16. So that's 65,536. Now out of those, we have 32,767 positive values, 32,768 negative values, and another 40. Add those together and we get 65,536. I hope it explains why there's this difference between the negative and the positive. The integers in Fortran are not quite standardized. So if you take some older Fortran, the integer can be 16-bit. If you take a newer, it can be 32. Who says it cannot be 64 bits, for example? If you're programming Fortran, know the size of the integer. There might be, I'm not sure if that exists, but there might be Fortran for some microcontrollers. And microcontrollers are usually as weak as this PDP-11 system. And they often have 16-bit chips in them. So there's a possibility that you will be dealing with 16-bit numbers, and there's a room here for an error, because if you need to count beyond 32,000, but you're using the 16-bit values, there's a possibility to make an error. And for now, we will move on to something more difficult, which will be the floating point values. In here, we have real value A, which starts at 1 again, and the old version of A. First, we print out in binary the following numbers. We print out 0, 1, -1, 2, 4, and we print out pi in binary, and we print out pi in decimal form. The second part of the code is the same as before. So we start with 0 and start to increment it over and over and over until something happens. Now what's going to happen? We will see. Either the number will decrease, or it will not change, or it will, if it will keep increasing, then we'll be having an infinite loop. But as we discussed before, it's impossible. Run it, and it runs much faster, by the way, than the previous test. And let's see how it works. So 0 is, not surprisingly, all bits are 0. It's very simple. Now 1 is already a mysterious combination of bits. So starts with 0, then another 0, and then some 1s, and then a whole trail of zeros. How is this 1? We will talk about it. -1. Now that's more or less self-explanatory. So the most significant bit, actually in this case, I cannot really call them most significant, because this one is the sign bit. In our system, this will be the 31st, starting from 0, the bit 31. Let's put it this way. It is 32nd, but it's, if we want number 2, there's a dramatic change here. Now there's only 1 bit set out of everything. And number 4, here's another one. And with pi, now we have something. Some sort of visible information, which pi is encoded here somewhere. Also, if we look at the number pi, really, it's not the same as we wrote in the code. It's not the same that we gave to the code. look at this. So we gave it 3.1415926. And what we get as a result, 3.1415925, and then a lot of gibberish. So at least one digit was lost. Now, as for the loop, so again, we started with 1 and we kept incrementing until something happened. And here's what happened. So the results that we get, the old A and the new A, are now identical. It's this very strange value. So if you think about it, it's on the order of 10 million. And this is its binary representation. And apparently, if you take this value, try to add 1 to it, it just doesn't happen. How curious is that? How interesting is that? Now, before we jump to the explanation of this, I'll just tell you that this is a feature more of the processor rather than the language. Because what the language does in this case, it takes these commands that we programmed, just passes them on to the processor. In contrast, when we looked at the spreadsheet example, what happens here is entirely different. So with a spreadsheet, it's made to calculate money. So it has to be precise. This cannot be any of this number trickery that we just encountered. Imagine if you enter like $1 trillion plus 50 million and you compute, and somehow your result is messed up because of the number system. As we saw, like in the very last digits of those numbers, you just get gibberish. Imagine how crazy that would be if you were, for example, in the government and you're adding the taxes that you collected from different companies, and in the end your number doesn't even add up. So let's just give it one more look again. In here, first of all, one thing to notice is it's way more precise, because here we can go to 10 to the minus 14. 10 to the minus 14, I can add. 10 to the minus 15 does not add. But how about 5 to the minus 15? 5 to the minus 15, it kind of rounds up to 1. Now, the point of this is that LibreOffice uses a special library for the arbitrary accuracy calculation. Arbitrary is not, in this case, random. In this case, it's set to the value that was intended by the programmer. So they decided, okay, we're going to compute it to the accuracy of minus 14, 10 to the minus 14. So it was decided by a programmer, and there's really no, in this case, there's no hardware limits. So welcome back. I will remind you that this material will be on the test. This is the kind of theoretical material that you need to understand really, really well. You will also need it for the problem sets. And in general, this is a fairly fundamental knowledge for any type of scientific computing, and even for non-scientific computing. Floating point arithmetic is used in video gaming. Whatever graphics you see, this is all computed in floating point. It's used in machine learning these days. Generally, there has been a lot of thought that people put into the floating point arithmetic. And we will see now, we'll talk a little bit about the history of it. If something is not clear after the lecture and you feel like you need to try to read it on your own, I refer you to the floating point arithmetic page on the Wikipedia, to any YouTube videos that you can find. There are some probably better explanations that I can give you. We'll just look at one specific case. That one specific case is this. It's a single precision floating point value, which is encoded in the IEEE 754 standard. Now, of course, there's floating point values with other sizes, so there's double precision, for example. And then there's other standards for encoding. We're looking at just one particular case on one particular system, but just looking at one example will already clarify a lot of things, just how things work and why we were getting those strange, seemingly strange results that we're getting. So here's the illustration on how this whole number is split. The 31st bit here is the sign bit, which we kind of already understood that flipping this bit will flip the sign of this whole number. Now, remember that for integers, it was not the same. This is only for the floating point representations, for reals. The next 8 bits here is what's called the exponent number. And the rest is the fraction number. In order to convert the binary into any system, decimal system or any other system that you'd like, we will use the following formula. So the sign bit is the sign. If it's 0, the result will be 1 minus 1 to the power of 0. What is it going to be? You should know. 1. So if the sign bit is 0, this expression disappears. It becomes 1. The next is the exponent. So to compute the exponent, we just take 8 bits that are in this green area and treat them as the integer representation of a number. So whatever exponent we take, we then subtract 127 from it, because 8 bits will give us 256 different combinations. And what we do here, we put 0 in the middle. So again, it's not the same idea as we had with integer values, because with integers, our 0 was everything, all the bits are 0. Here, we take this exponent value e, but what the number that we will use afterwards will have 127 subtracted. So the 0 exponent here is not all the bytes set to 0, all the bits set to 0, but it will be pretty much all except the leftmost one. So we'll have the value of 127 will represent an exponent 0 for us. And then the rest is the actual number, so to speak. Well, of course, this whole formula is the actual number, but we already saw that the first is the sign, then there is a multiplication for the exponent, and then the rest is for the digits. Now they come in this form of a sum. 1 is always there. There's a sum, the value of each bit multiplied by 2 to this negative I. What does it really give us? Let's look at the example. Another example, something that I prepared here in Mathematica. So let's look at the Mathematica worksheet that I prepared for you. I hope just to make it, I know it looks very scary, but it's prepared to be more sort of explanatory about how things work. So this expression that you saw on the Wikipedia page is now in the form of the Mathematica function that is split into several pieces. So we have the sign, the exponent e, and the fractional part f. Now the expression is the same as in Wikipedia. Let's try to plug in something in there. We'll plug in the value for pi. The value for pi is the one that, well, I had printed out. So it's this last one on the list. So 0 for the sign. Now 1, 2, 3, 4, 5, 6, 7, 8. These numbers for the exponent, and the rest for the fraction. What I'll do, I'll just copy paste them into Mathematica like this. So these for the exponent, this for the fraction, and they will go into the formula. evaluate notebook. The exact value of this expression is this rational number, 6,588,397 over 2,097,152. Why is it a fraction? Because this whole expression is a fraction. It's a sum of 1 over 2, 1 over 4, 1 over 8, and so on and so on. So all these portions are fractional. Now this is a multiplier of some sort, and that's another multiplier which can give it a negative sign. The point is, in this whole expression, there is nothing that takes it out of the set of fractions. It's a numerator over a denominator, always. So every time it will just give us a rational sort of approximation of pi. Now, you probably heard that pi is not a rational number, it's irrational. There's a mathematical proof, it's fairly complicated. Every rational number is a repeating decimal. So there will be a decimal representation, but at some point this tail of numbers will repeat over and over and over again. Now the length may be quite large before it repeats. Let's try to print out 100 and see if we can spot. And indeed, it actually does repeat. We have this 0 at the end, and it just continues. But this is kind of what the Fortran printed out for us. Let's look at this. So it printed 9250259, and we'll look here. It's 9250259. And the rest will be, let's compare. So you see it actually printed out exactly that. So to some extent, now the mystery is solved. Why the pi number is no longer a pi. Why its value changed. We gave it one thing, it printed out the other. Let's just give it one more look to just ensure that we understand exactly what's going on. So how this expression, if you write out this sum in detail, how is this expression is going to look like? And this is the result of this. So first, exponent part. And if we just take the exponent itself, 2 to the power of 1, which is 2. And then the rest, this tail, comes from this sum. But only the components that are non-zero are included. So let's look at this. We'll start with this one. This will signify that we have 1/2 included over here. And then 1/4, 1/8 is not. 1/16 is included. 1/32, 1/64, 1/128 is included, and so on and so forth. So we only have the components which have ones in them. Only those are added together. So let's talk about the consequences of this type of encoding. So first thing to notice, the range of numbers that this can cover is quite large. So we're talking the exponents on the order of 2 to the power of minus 127. And that becomes around 10 to the power of minus 39. So those will be on the smaller side of values. To the power of about 2 to the power of 127. So that's 10 to the power of 38. So the numbers can cover like minuscule tiny values and also fairly large values, which was needed in science because scientists, they like to speak about like atomic scales and the scales of galaxies, and they need some tools to deal with like small values and big values. Now, if we multiply these values, there's really no problem. Let's try that. Let's just try a few things. So first, can we have a number which is 10 to the power of minus 37, for example? Another, what we can try, let's take this and multiply it by 10 to the power of 10. Can this work? To take it more to the extreme, can we multiply it by the power of, actually no, we cannot. But let's multiply it by 10 to the power of 20. And then multiply it again by the power of 10 to the power of 20. And let's see if this works. And indeed it does. So the first number, as expected, something to the power of 37, minus 37, works great. Another, this multiplication gave us, again as expected, 10 to the minus 26. The last one gave us 1000. Now similarly, we can have a number which will go 10 to the power 38. So a fairly large range is covered. One thing to keep in mind, as we already established before, if you try to add 1 to something, if it's less than 10 million, it will make this difference. So 1 plus 1 million will be 1,000,001. Now 1 plus 100 million will not change anything, because as your numbers grow bigger and bigger and its exponent is an order of magnitude, you're losing that relative precision there. And it's illustrated on Wikipedia with this plot. So when you're close to 0, you have a fairly high resolution between the subsequent elements of that set. And as you move further away, you cannot have any numbers in between. So only when the green lines are drawn, those are the values that you can have, and there is no way to place 1 in between those green lines. So this is the feature of this system. There's another plot over here. So for example, when we're talking about 8 million, so you can have 8 million something 608, and you can have 8,388,609, and even 610 and 611, 612. But then at some point, here's the one that's marked black, and you just cannot have the representation of this number. There is just no set of bits that will give this particular value to you. The next available will be 6,177,218. So now we're skipping 1, right? So 19 we skip. The next will be 220, and so on and so on, until we reach 33 million something. And then we will skip 4 values. That's just the feature of this counting system. So as the numbers gets bigger, it loses resolution in numbers. And if you think about it, it kind of makes sense, even like from the perspective of the video games, because let's say you're looking at the object up close, perhaps some body parts of the players, and you need the very fine resolution to see what's in here. If you're looking far away in the distance, there's some buildings, there's some mountains. You don't need this 1 centimeter or even 1 millimeter resolution for the mountains that are displayed somewhere all the way in the background. Those mountains, maybe, of course, the artists, they drew them, but when they are that far away, the resolution there is lost. So that's the way that how this number system works. And then there's finally a few more things to mention in the topic of this lecture, is that there might be some combination of bits that do not make any number at all. For example, those will be something called not a number, NaN, and there will be infinity, and there will be negative infinity, and so on. So, for example, this combination of bits will result in the value that will be interpreted by the processor as infinity. The trick there, it will still perform algebraic operations with it, but if you add infinity with anything, it will just remain infinity. There is also negative 0, as we noticed before, and there's also negative infinity. And then there's some representations that give you something that's called not a number. And they usually result from something like, if you're trying to evaluate, for example, like a logarithm of negative value or a square root of negative value, then it cannot possibly return a reasonable result. So not a number, it just means it's a gibberish combination of bits that's not supposed even to work. Whatever you do with not a number, you try to compare it, it will always compare as false. Even if you try to compare two not a numbers, they will just be always false. If you try to multiply it with anything, it will just remain not a number. Multiply, add, any mathematical operations. Now, next lecture, we will talk more about numbers. We will still have to touch on hexadecimal representations. The topic of representing the numbers for the computing and what the computer does with the numbers, it's very fundamental in terms of computer science in general, in terms of computation. So unfortunately, it will be something that will persist throughout this course. We will see the effects of it once in a while, and we'll have to talk more about it. This is the end of lecture 4. Thank you very much.